学校外面也太慷慨了吧？就是明明看起来就是去凑那个多一天放，对，爽放一天这种感觉，我不懂。不过他不知道有小孩子的人这么爱工作吗？哎，我最近就在今天我才看到 PTT，我是乡民了哈，我是 PTT，然后我在 PTT 上看到那个有人真的是开心的上班吗？然后上面就写说，哦，大家看捷运上的人都是一脸死相啊，什么什么之类的啊，很难过啊，什么什么，谁真的很真心自己喜欢上班嘛？然后下面就一大堆回文嘛，推文推到后来就有一个人说，你生了小孩你就知道你有多爱上班了，完全正确啊，完全正确。就是我现在觉得上班是休息，回到家才是工作，真的是这样。因为你上班就是真的有自己的时间，然后尤其是我啦，我还有自己的办公室嘛，那我没课的时候我可以自行运用我的时间，那所以我还蛮喜欢教授这个职位的，虽然他赚的不多了。你知道未来大家就是大部分的同学都会赚的比我多吗？我的所有的毕业生大概90%都赚的比我还要多，真的真的。他们可以去台积电啊，说我可以年薪大概200-300万这样，好棒，这样真好。但是我的工作是自由啦，就你可以偶尔看到我在走在路上，在上班时间走在路上去喝杯麦当劳啊，或是跑跑步啊，这我就觉得这是一个自由无价啊，这是我对于就是我的工作的那个好，OK，so let's continue。还在那边讲说教不完，还在那边打嘞。OK，let's go. So welcome for this course and good morning and thank you for coming. So next, I will talk about the non-uniform torsion. In the previous few hours from yesterday's, we talk about pure torsion, right? But now we talk about non-uniform torsion. So which means that torsion may change, right? But don't worry about that because you have encountered similar problem in chapter 2. So for example, you have changed cross section. The bar changing the cross section is non-prismatic bar. And also you may have T1, T2, T3, and T4. Okay, and you notice that they have this material has two cross-section area. So if you want to determine the total twist of angle of twist, okay, twist angle, okay, how should we do? I believe you understand that if you know the detail of chapter 2. I need to calculate every the twist angle for each section. So there are 3 sections in this material. So the first one is this one. I cut here, and this is my cut, and I leave left hand side. Okay, so the T3 looks like that, T2 is here, and T1 is here. And of course, there must be an internal torsion called TCD. And the direction I just assume to the positive direction. And you can see that TCD, and this is T3 is going to left hand side, right? And T2 using your right hand, okay? It's from left hand side, and there's a right hand side, left hand side. So T3 is the one it with the positive opposite direction. So TCT equal to minus T1 minus T2 plus T3. Okay, so you notice that you just need to use in the concept in chapter 2. you can have TCD. It's the torsion within this section. Okay, and then the second section is here. The second section we're using blue. I cut it and leave left hand side, and the left hand side with the T2 and T1 and TBC. And TBC and T2 and T1 are all the same direction. So you will see TBC has equal to minus T1 minus T2. And the third one, pink, I cut it and we left hand side, and you will have TAB assume to the right hand side, I mean right direction, and T1 appeared, so TAB equal to minus T1. Okay, so you have internal torsion in the 3 sections. So each shear force in each segment is TCD, right? So TR divided by IP, you can obtain tau, and if you have tau, and also you can have phi equal to TL divided by GIP. Of course, IP, this one has its own IP. This two has the same IP, but this one has a smaller IP. Okay, so you have 3 sections, you have 3 phi, and you sum them together become total angle of twist. Easy, right? The concept is easy. Okay, so you can expect what I will going to introduce in the next page, because you can notice that if we have a gradually changed cross section, so all you need to do is changing its IP and do the integration from for the entire length. Or if you have a torque TA and TB and changing cross section, and of course maybe your torque changing as well. Torsion changing through the length. So of course, what you're going to do is do the TX. You need to determine the TX in the between the DX length, and then if you want to determine the T of X, all you need to do is just cut it, and then do the balance, so you can have TX. So you have TX, and you do the integration from 0 to L, and of course IP needs to be written as a function of X. So that's basically what you learned from the chapter 2. But please notice that only apply for bar with circular cross section, as we mentioned before, because this formula was proved by assuming circular section, right? So basically, this is really similar to chapter 2. I believe all of you understand this. Next, I will going to give you a example to let you practice, but I believe this is not difficult for you. Okay, next one. So this is a problem that left hand side and right hand side, A and E point are free end. So, and T1 has a gear, T2 has another gear, T3 another gear. So these, we are talking about equilibrium state, right? So T1, T2, T3 well balanced, okay, well balanced, mutually balanced. And then it's D is the material, blue bar, materials D equal to 30 millimeter, LBC 500, LCD 400, T1 275, T2 450, T3 175, G equal to 80 G par. So it needs us to calculate maximal shear stress in each part of the shaft. So what does it mean? Max shear, maximal shear. Maximal shear, of course, I believe you notice that we explain this because it's on surface, right? It will be on surface and each part of the shaft. So each part, what does that mean? It means that BC and CD segment, right? So BC and CD, these two segments. So yeah, that's it. So first things, I want to determine the internal torsion in BC, internal torsion in CD. So what should I do? Just cut it, right? Just cut it, cut it, cut it. So this is blue and this is light blue. And I decide to leave left hand side. So dun, dun, and I assume TCD is in the right position, right direction, positive. And TBC, of course, positive. We assume that. And T1 is here. Okay, so now, so TCD equal to T2 minus T1 equal to 450 minus 275. So it should be 175 Newton times N. TBC equal to minus T1, 1 equal to minus 275 Newton. Okay, so you see that the TBC, we had wrong assumption, okay? But it's okay. We know the number. So now we know the portion in the section. So maximal shear stress, maximal shear stress. Okay, tau equal to TR IP equal to 16T IDQ. So tau BC equal to 16 times 275 and pi 0.033 and phi 1.6 and pi. Maybe you will say why we don't have negative sign here. Negative sign. Why we don't have negative sign here? Because it's okay. Because we are going to determine the maximal shear stress. And you know that the maximal stress come in pairs. So it's either you can talk about positive or negative, it's all okay. Because when we talk about something like this, right? And this is positive shear, but in this direction, it becomes negative. So basically, they are all the same. Shear, shear. They come in pairs. So all we cared here is maximal shear stress value. Okay. So of course you can write down here minus, and you get minus, but it's okay. It just talk about different direction. Sorry, different directions, right? So it doesn't matter. Tau CD 16 times 175 by 0.033 equal to 33.0 MPa. Okay, so this is the BC part and CD part, and you will have 51.9 and 33.0 MPa. So this is maximum shear stress, or you can say the shear stress on the surface. The second one is angle of twist between BD, phi BD, right? Phi BD. So what is phi BD? Phi BD equal to phi BC plus phi CD. And we also know IP equal to pi D4 divided by 32 and pi 0.034 divided by 32, which is 7.952 times 10 to minus 8 m 2 power by 4. So phi BD equal to minus 27. Okay, you see that now it matters. Now it matters. Minus 275, because now we talk about the total angle of twist, right? So if you have different direction of the twist, they will cancel each other. So this needs to be considered. Minus 80 times 10 to 9, 7.952 minus 8 plus 175. So you see negative 275 and positive 175. So which means that their angle of twist will cancel each other. Okay. So equal to minus 0.0106, approximately equal to minus 0.61 degree. Okay, that's it. That's the practice. I believe this is easy for you, right? This is very similar to chapter 2.那怎么了？啊？最后边下面怎么了？数字不一样。对，一个是 degree，一个是 radian，这是度。OK，sorry，zero minus 0.71 degree。degree。degree. Is that okay? Sorry. Oh, by the way, do you know people from different countries write numerical, write number in different style? Did you notice that? For example, when I study in the UK, I draw. I write down numbers, and my supervisor cannot understand. He's British, so for example, I write down like this one. What's that? What's that? If I write this, what's that? This one. 2. Number, it's number. So when I say 2, 2, 5, 8. 2, 5, 8, right? Or I say 2, 5, 8, or 2, 5, 8. Okay, something like that. But my supervisor don't understand this, because in their mind, they're writing the number need to be really specific. 2 need to be this one. 5 need to be this. and 8. Okay, so if you write down in these things, they won't understand. They won't understand, literally. Okay, so I said, oh, I think they are the same. No, he said, no, I don't think they are the same. Okay, this is really interesting. Right, that's it. So sometimes when we think, we make our writing become, I don't know, maybe I thought it's elegant or good looking, but other people from other country will think this is not 2, this is not 5, right? Because they cannot recognize this and that, and why it become the vertical lines. So they really don't understand. This is really interesting. 应该听懂我在讲什么吧？哈，好，就是我们以为写的很漂亮，没有，他们会觉得我在乱写。对。Okay, next one, very important, but the concept is really similar to chapter 2, so don't worry about that. Okay. Stress on incline section again, but now today we're going to talk about the stress due to the torsion. Okay, so now I'm going to draw a bar for you. This is a bar, and now because we are going to introduce this stress element, we want to make the main surface has positive stress. So we need to let you understand actually what kind of torsion makes this element. Okay, so basically, actually, you need to apply this torsion to make the stress element undergone positive shear for the main surface. And this is come in pairs, right? Come in pairs. Okay, so why? Because when you have the torsion direction from the left-hand side, which means that you do that, right? So that. Okay, and the other side, right-hand side. Okay, so it is. Okay, so the pink arrow is actually due to the double arrows torsion, right? And then you found that because it twists in this direction and the left-hand side become that direction, so it will make this part go up, this part go down. So you are generating the stress element like this. Okay, so why we are going to using this? Because we are going to write down a stress component formula, because we want to have a good starting point that our 0 degree sigma x 0 degree has positive tau. Okay, to make everything in our sine convention rule. OK， 为了让第一个就是正向的第一个主角面，它的 stress， 它的 shear stress 是正的，这样我们等下推导过来都是正的，这样比较好推。那既然这样子的话，我们就必须要这样子做法。那这样做法就只能它的那个涛是这样子了。所以说一开始我们如果从这边开始想象，我们会我们要把这个涛把它往外，这样对，好，我们通常都会这样，但是这样会变成这边一开始往下，那这样对后面的推导就会变得很困难，因为它多一个负号。Okay, so actually the reason why we're going to introduce this kind of, which is different from our previous assumption, is because we want to make this surface has positive shear. Okay, so now we have stress like shear stress, and we want to find the stress on inclined section. of course, previously we have x and y. Now we're going to have a incline theta, incline theta. So if you have the theta here, which means that your x1 will has the theta angle between x1 and x. Okay, so and then you can have a triangle, and we cut this triangle to here. Okay, so this triangle is equal to this one. All right, I'll just move this to here. Although they're not exactly the same, but please pretend that they are the same. Okay, so now if we cut it, because we want to see the stress on incline section, we want to see this section. What is the stress on that section? We just cut it and put here, and we leave left-hand side. So this tau is this tau, no problem. This tau is this tau, no problem. But we cut it, and we need to write down two stresses. The first one is normal stresses, sigma theta, right? This is tau theta. And then because we leave this part and we ignore this part, so we won't see this tau, right? So now we want to do the balance, force balance. And before we do the force balance, we need to times the stress by area, right? So what is area? So area here, A0. A0. Okay, because this is entire element. So the stress element has A0 for each surfaces, for each surface. So A0, nothing changed. But this one is relatively smaller than the A0. So what will it be? It will be A0 tangent theta, right? And how about the incline section, incline surface, A0 sec tangent second，哎，是这样念吗？我很脑袋打结了。tangent SEC 怎么念啊？完蛋了，second 嘛，哦，second 啊，哇，好恐怖哦！我昨天看到一个广告，让我觉得非常的 shock。我不知道是广告还是电影啊，反正总之就是有一个怀孕的女生坐在公车站，我不知道大家有没有看过，我也不知道为什么他要推播我这个东西，在 IG 在乱滑的时候，就有一个怀孕的女生坐在那边，她看起来满脸愁容，然后旁边就有个老先生，老先生就忽然转过来问她，就跟她搭讪，就跟她说：“哎，你怀孕多久啦？”然后那个女生就看这样子，然后看他一下，看那个老先生一下，然后他就说，他就有一点不想讲，然后他那个老先生就，哦，好好好好，我不打扰你。但是后来那女生还是跟他讲，他就说怀孕21周了，然后那老先生就说，哇，那快要生产了，你一定很高兴吧？然后他就说，那女生就说，并没有很高兴，因为我们家就只剩我跟我爸爸了，然后我爸爸还生病，然后他爸爸就说，哦，真糟糕，我不是讲错了，我啊，糟糕，我讲出来，反正那个老先生就说，哦，真糟糕，这一切都会，it will be all right，这样，真的。然后这时候公车就来了，然后那女的就站起来要上车，他就说，爸，走了。那个男的是他爸，那个老先生是他爸，好惨啊，怎么惨啊？哎，对，就觉得，然后我刚刚竟然忘记 second 怎么念了，这是失智症的一个倾向啊，真糟糕。好，那对啊，然后还有我最近其实很久以前了，最近这之前也有看到一句话， 就是好像就用很简单的话去讲一个故事，就可能5个字的故事，用英文讲故事。然后我那时候看，我想说，好像还就是有一个我就觉得超强的，他就说就5个字英文，我忘记是什么，但是他就是说 baby shoes for sale，括弧 unused。超惨的一句话，你可以想象吗？Baby shoes，baby shoes on sale，括弧 unused，超惨的一句话，你可以想象吗？为什么？对，他们原本准备了，小孩没有生下来，然后对，然后呢，小孩的鞋其实应该算是便宜的，然后他还要卖掉，可是他没钱，好惨哦，超惨的，就这样，没带，对。然后当了爸爸以后，对于这种就很有感触，好可怜的。好，OK，Anyway，开始吧。So we have a different cross-section area, and then we need to times their stress and become force, and then we can balance. Okay, so please don't say stress balance. No, no, no. Force balance. You need to times their area and then you can do balance. All right. So here, sigma theta, A0 section, second theta, A no second theta with tau theta. And this one and that one times tau A no and tau A no 10 theta. But we need to, because we need to balance, right, in the same direction. So we need to do that. 我刚竟然把他是他爸爸讲出来，我真的是蠢到爆！竟然这种 punch line 竟然就啊，效果还是这样，谢谢你，我真的觉得你们都很捧场，谢谢你。你知道我每次看到那些，我最近不是最近，其实我一直都很喜欢看那种单口相声，就是 stand up comedy 就对了。然后他就在那边讲话，我就觉得其实如果今天一个老师可以跟他们一样强的话，那你们上课应该会很开心、很有趣，对不对？那但是我真的觉得这很难做得到，因为就是要让大家笑实在是太难了。那你知道我们学校有一个老师，他要去参加爬米蒂 open m i d 吗？陈俊泰老师有听过吗？我就觉得他超有勇气，超强，就是他站在台上就是要，我觉得超难的，真的超难的。啊，就这样，我就觉得我很佩服他，因为他还有进决赛啊什么之类的，强真的是佩服。Okay, so you have two directions and then yeah, very easy. Let's go. So tau theta anal section theta second theta here. Okay, and then equal to this one and that one. This one and that one is tau anal sine theta, and tau anal tangent theta cosine theta. This one. Okay, no problem. And then you can have sigma theta equal to blah, 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 equal to tau sine 2 theta. So in inclined normal direction, you have sigma theta equal to tau sine 2 theta. So if you have pure shear stress, your stress component in inclined section is sigma theta equal to tau sine 2 theta. And in incline, sorry, it shouldn't be normal. Uh, incline, uh, implant, implant direction. Okay, implant direction. Tau theta anal section theta equal to this one tau anal tangent theta, and this one tau anal cosine theta, and equal to tau theta equal to tau cosine 2 theta. Oh, it's just relatively easy to remember. Okay, so easy, but maybe, well, I will tell you 90% of proof in proof problem in mechanics of materials typically just choosing right area and times its stress and then do the force balance. 90%. So when you think about that, it's kind of easy. 90%. Okay, so if you have if you successfully get this formulation, again, we can examine its maxima and minima because they have cosine and sine, right? So sigma theta sine 2 theta has its greatest value in half pi. No, it's not half pi. 45 degree, and 45 degree. Okay, so you have 45 degree maxima, and the tau theta is 90 degree and 0 degree. So this one is in this part. Okay, you see in the 0 degree, this one. 0 degree means that one. Okay, so maybe I can give you a hint. Okay, this one is that one. Okay, and interestingly, this one is this one. Right? You see how 0 degree, your focus surface, your main surface is 0 degree. Okay, this one. And of course, no normal stress. Normal sigma theta equal to 0. And in this one is, if you focus on this one, your head will do like that, right? And this one is focused. So this is my, oh sorry, it should be in this position. Sorry. This is 90 degree. Okay, so 90 degree here, negative shear, because this is x1 positive direction, but this is minus y1 direction. So positive and minus become minus. So this is minus. So that's it. And also, if you have greatest 45 degree, and you will have zero stress, zero shear stress, but you have greatest sigma max, which get tau, So the tau is the value, okay? Although the value tau, which now is the sigma max, is normal stress, okay? 这边要小心，虽然这边写 sigma max 等于 tau， 你会觉得，哎 ，sigma max 不是 normal 吗 ？tau 不是 shear 吗？哎，没有啦，这个 tau 其实是 shear stress 的值，这个的值。所以说他的意思是说，它的在45度角的话，它的 normal stress 正向应力的值刚好等于你施加这个剪力的值。OK， 所以不要以为说，为什么正向应力会等于剪力？没有，是剪切应力，没有，是剪切应力的值。OK，only the value. This is value only. Okay, so sigma max equal to tau because it's like that. So you can imagine that I've talked about yesterday. A material with weak tensile strength, which is concrete, right? And the concrete in this 45 degree, it will subjected to the highest tensile if you have the torsion on it. So you will always have 45 degree cracks and you will have this one, okay? You can try it. If you have, I don't know, maybe you can make a competition for your classmates and you can to see which one can generate this kind of crack. All right, so this is the stress on the inclined sections due to the pure shear. So next one is strain in pure shear. So now you will have a stress element undergone shear stress tau. So you have a 平行四边形. Okay, the shape like this. So the tau equal to G gamma. The gamma, of course, is the stress. No, sorry, shear strain. The changing of the angle. So you see here, previously it is 90 degree, but now it become half pi minus gamma. So you can imagine that. Oh. So you can see that. So you can see that. Okay. So this one, and that one is half gamma. Okay. So this is the shear strength. And if you have the 45 degree, if you changing your square, when you draw the square, you're not drawing like this. You draw in the 45 degree, and you do the torsion. Actually, it will deform into a dashed square, dashed rectangle. Okay, so which means that actually the deformation is compression in this direction and tension in this direction. Okay, and we say this is tau, this is minus tau. Okay, so let's take a look. What kind of strain will it be? So the epsilon mix, well, you can say this direction. Okay, the epsilon mix equal to tau mix equal to this tau is sigma mix. The sigma mix divided by E, and the sigma mix, the value of sigma mix is tau, right? And the second term, there are two contributions to make this deformation. The first one is sigma mix caused by sigma mix, pooled caused by sigma mix. But another contribution is the side pressure caused by the Poisson ratio. So the tau, this one, it is Poisson ratio. Okay. So when you combine them together, you have epsilon mix equal to tau divided by E times 1 plus nu. The nu is Poisson ratio. 好，这边要稍微讲一下好了哈，就是说你一开始画如果是这样的画的话，你得到你用纯扭的话，它就会变成这样子。OK， 那如果你今天同样的状况下，你不要画这样子，你画的是斜45度角的方块的话，你这样照样扭下去，你会得到虚线的这样的形状。OK， 那虚线这样的形状这边你刚刚也看到，在45度角的地方，它会有 sigma max， 那 max 的值是 tau 啊，然后它会有一个拉力，这边有个压力。好，那我们来看看它的 strain， 这方面的这个方向的 strain 呢，会有两个贡献，谁贡献它呢？一个贡献是直接就这样拉上去的 tau， 另外一个是压的剖松比，又会贡献一点点在这边。OK， 所以有两个贡献，第一个贡献就是 sigma max， 那当然这边写 tau 的意思就是它其实就是 sigma max 啊，就这个 sigma max，sigma max divided by 1，这是第一个 term， 是因为拉的关系。第二个是旁边造成的，旁边压下去以后，你有剖松比，所以是 tau divided by 1，这个 tau 是这个 tau 哦，那这个 tau 可能会有这个负 tau， 但是因为普通比啊弄来弄去就变成负号，就变正的了哈。那总之就加 nu tau divide by 1。那这个 nu 当然就是之前的普通比吧哈。你这边的应力，这边的应变乘上去以后，就会是它这边的贡献，好，这个方向的贡献，加起来以后，这个 epsilon max 这边的 epsilon max 是 tau 除以1乘上1加 nu，OK？So that's it. And if you understand this, we will know that after pure shear, pure torsion, your 45-degree epsilon max will have two contribution. The first one, the tension. The other is the compression, and also the Poisson ratio effect. Okay, next one. Now, I will going to introduce a relatively difficult thing, and then maybe I need to talk about that after this quiz. Okay, I think I don't have time. Right. So see you next time. Next week, next Tuesday, we will have quiz. Okay, 40 minutes. So be careful. Bye.